Well, good evening, ladies and gentlemen, and welcome to Gresham College. Especially if this is your first visit here, we have the 12th of the British Society of History of Mathematics joint lectures with Gresham College. These were started in the year 2000, and the idea for a whole series was due to John Favell. He suggested that we had a whole series of these things, and they have been about once a year ever since. I won't go through the list of all the former speakers. We have had a very distinguished succession of talks, and you can see them listed on the flyer that we've handed out. Today's speaker is particularly distinguished, Dr. Peter Neumann. Studied at Queen's College, Oxford, where he subsequently became a junior research fellow and then a tutorial fellow, retiring from there just a couple of years ago. After his retirement, he went to Paris to work on his book on Évariste Galois, which you can see over there afterwards if you wish, and about which he's going to be talking tonight. He's won a number of prizes, the Lester Ford Award by the Mathematical Association of America in 1987, and very prestigiously the Senior Whitehead Prize of the London Mathematical Society in 2003. He has been chairman of the UK Mathematics Trust and has served on the Council of the London Mathematical Society, and in 2008 he was awarded an OBE for services to education. It is a particular delight to introduce my old friend Peter Neumann tonight to talk on the memoirs and the legacy of Évariste Galois. Peter.
Thank you. Thank you, Robin. Thank you. It's a very great honour to be here. It's also necessary that I should be here because otherwise Robin did not have anywhere to sit. He told a lie. He doesn't often do that. I'm certainly not going to tell you about the book that I have just published last week. It's a technical monograph. I'm going to urge you to buy it, but that's a different matter. I'm not going to tell you about it. It's a technical monograph, a scholarly monograph. It's an edition of the writings of Galois with commentary. Commentary essentially trying to establish both a French and an English version of his writings. So it's not the sort of, well, it's the sort of book that could send you to sleep. I have a problem with you as audience because I was told to lecture to a general audience, and that is what my instinct suggests. But I also know there are those among you who have a lot of mathematics. I'm going to try to lecture to the intelligent public, but there will be a little bit of mathematics in there. Now, you remember when you get to the dentist's chair, the dentist says, if you need to catch my eye, this is while you've got a drill in your mouth and you certainly can't shout at him, you raise your hand. Will you promise to do that if you find that I'm going way over your head? Do you promise? Robin, you promise. On behalf of everybody. Yeah, good, good, good. Évariste Galois. Little lad, rather obnoxious little lad, actually. Here's a brief curriculum vitae for him. The excitement last week was that this was the 200th anniversary of his birth last Tuesday. He was born on the 25th of October 1811 in Bourg-la-Reine, which is now just one of those maybe nondescript sort of suburbs south of Paris, except that they're having great celebrations to celebrate their famous son. It's about 10 kilometers south of the center of Paris. and his father was a school teacher there and also mayor of the community. The next date I've given you, October 1823, he entered the Collège Louis-le-Grand, which is right opposite the Sorbonne on the Rue Saint-Jacques in Paris, stayed 6 years. I discovered last week, on Thursday, that particular date, October 1823, is now debatable. Now, any of the dates that I've put down here are debatable. I've found contradictory evidence for all of them, pretty well all of them, not quite all of them. So when I say entered October 1823, remember this, that some friends of mine in Paris, in particular a retired history teacher from the Collège Louis-le-Grand, has found the entrance book in which his entrance to the collège is recorded as being 1st of April 1824. And that's particularly interesting, but we don't yet quite know what to make of it. Anyway, he started submitting mathematical discoveries to the Academy when he was really quite young, but unfortunately, 1829, his father committed suicide, and this was a huge blow for Évariste. He tried twice for entrance to the Grande École, the École Polytechnique, and failed twice, and managed to pass the entrance for the École Préparatoire, it was then called. It was the École Normale until a couple of years before. For a very short time, it was called the École Préparatoire, the preparatory school for training school teachers. It's reverted to being the École Normale in 1830 or 31, actually I think 1831, and became what is now the very famous École Normale Supérieure in 1845. I said he submitted his mathematical discoveries to the Academy in May 1829. He submitted them to the Academy again in 1830 in competition for the Grand Prix de Mathématiques, but that manuscript was lost. On the advice of Poisson, he submitted for a third time. And this was on the 17th of January 1831, shortly after he'd been expelled from the École Préparatoire. Soon after that, he was arrested for offensive behavior, but he was acquitted. Then, on the 4th of July, the premier mémoire, the memoir that he had submitted to the Academy, was rejected by the Academy. 14th of July, Bastille Day, he was celebrating, and he was arrested on the Pont Neuf in Paris, and charged with wearing the band uniform of the National Guard, but also, more stupidly, well, both were pretty stupid, carrying loaded firearms. He was imprisoned for 9 months in the Prison Sainte-Pélagie, released towards the end of April when there was an epidemic of cholera in Paris, and it was safer for prisoners to be released to safe houses. And he went to the Maison de Monsieur Fautrier, where he lived during May, got himself involved in a duel at the end of May, went out in the morning on the 30th of May, was shot and died the following day. Well, so why should we care about him? Some little silly boy who goes off and gets himself shot for no reason at all. But here he is, Évariste Galois, révolutionnaire et géomètre. That's the title of a novel by André Dalmas, one of the great French writers. This one was written in 1956, and there was a second edition in 1982. You see there, it's a postage stamp which Robin very kindly gave to me. It says, up at the top there, you can see just see Évariste Galois, 1811-1832, and then down underneath the smaller portrait, the inset portrait, révolutionnaire et géomètre, revolutionary and mathematician. He is highly regarded by the French as a revolutionary. But I have to say that, looking at his record, I find him totally incompetent as a revolutionary. All he did was spend time in prison. However, as a géomètre, as a mathematician, he was revolutionary, truly revolutionary. I've called this the Memoirs of Évariste Galois. A little lad who dies aged 20 doesn't write his memoirs. But of course, the word mémoire means memoir, paper, article, meant it then, as it does now, though it's sort of old-fashioned language now. The first, sur la théorie des nombres, on the theory of numbers, published in June 1830. June 1830. June 1830. Remember, he was going to be 20 in October 1831, wasn't he? So he's still 18 when this is published. He's 18 and a half. There's the Mémoires sur les conditions de résolubilité des équations par radicaux, the memoir on the conditions for solubility of equations by radicals. It's known now as the premier mémoire, the first memoir. That's a name, an informal name, of course, but it's a name that Galois gave to it in several of his writings. I'll come back to that in a minute. It's an amazing document. It contains what we now call Galois theory of equations. It was rejected in July 1831, 4th of July 1831, by the two referees appointed by the Academy, Poisson and Lacroix. Their report makes very interesting reading. It's a very sober report. It's a very sympathetic report. But it points out that they haven't been able to understand it. And if they couldn't understand it, then he ought to go back, write it more carefully, write more of what he knows, and it would be all right. That's what they write. Well, of course, Galois got a bit cross and stroppy, and of course, history has since then given Poisson, who wrote the report, a bad time. It's a bad thing to have recommended a rejection of an article which later just changes mathematics. So with hindsight, we see that Poisson was wrong. But if you go and look at the paper and you go and look at the report, you begin to have a lot of sympathy for Poisson. And I'm not the only one. I should say the great Jacques Tietz, one of your heroes. He went on record 20 years ago in the Academy saying that he began to understand Poisson and he sided with Poisson. There's des équations primitives qui sont solubles par radicaux, known as the second memoir. This is a very, very difficult document. I've worked on it, but I have lots more work to do on it. I have a whole lifetime's work to do on it, and that would be true if I were 21, which I'm not, unfortunately. Like the premier mémoire, it was first published in 1846. So we're talking here 14 years after Galois' death. Then republished many times. Published in German in 1889, published again in France in 1897, published again in 1951, again in 1962, in 1984, and now you have a publication of it, my transcription of it in that book, 2011. Same with the so-called memoir. Same with this fantastic letter. On the eve of his death, famously, Galois, instead of practicing his shooting or getting an early night, stayed up, wrote a wonderful letter to his friend Auguste Chevalier. Mon cher ami, he writes. And he summarizes everything that he knew. The paper, the letter is not very long. Well, it's not very long for its content. It's essentially 2 pages folded double, so it would be 8 pages. The last page, however, has a rectangular part of it torn out, and on the reverse of it is a very mysterious document that seems to be a transcription of a letter to a girl or something. Very, very mysterious. So in fact, it's 6.5 pages long. But those 6.5 pages contain more mathematics than any other 6.5 pages you can imagine. And it's very beautiful. Then also he had a few articles published when he was 17 and 18. Those published articles, of course, were there in the record. The manuscripts were left on his desk. They were collected, I think, by Chevalier, possibly by Galois' mother, and then given to Chevalier after the duel. In due course, Chevalier gave them to Liouville. Liouville gave them to his son-in-law, Monsieur de Blinière. Blinière gave them to the Académie des Sciences. So they came to the Académie des Sciences in 1905, and they're now in the library of the Institut de France, which is a union of the libraries of the Académie des Sciences, des Beaux-Arts, and so on, bound as 1 volume. There are about 285 folios, of which about 200 are in Galois' hand. But remember, some of these are tiny little scraps with all sorts of jottings and calculations on, inconsequential, very hard to see where they fit. There's a huge jigsaw puzzle to be solved there. They're organized into dossiers, and the first few are the important ones. Dossier 1 is the Premier Memoir, the great article rejected by the Academy, but which, when it was published in 1846, gave what we now call Galois theory to the world. The second is the original of the Lettres Testamentaires. Puzzles me somewhat, because I do not know why we do not have a copy in the hand of Auguste Chevalier, but that's another story. Dossier 3 is a copy by Chevalier of the Premier Memoir. It's the one that was used by the printer in 1843 and then 1846. And it also contains some material by Liouville. Dossier 4 is the Second Memoir, this very difficult article that was never completed, that goes wrong, that is a very mysterious document, but it contains some wonderfully deep mathematics, some glorious insights in it, long way ahead of his time. And then Dossier 5 is a copy by Chevalier of the second memoir, and all the rest are fragments. Some is interesting mathematics, some is philosophical polemical writing, of which some, I'm afraid, is horrid. And there are scraps with unexplained calculations and jottings, and so on. There have been many editions. And as I said before, mine is the last one. It is an edition. It's supposed to be a scholarly work, as scholarly as I could make it. They were first published by Liouville in 1846, and as I said before, they were published again in French by Picard, Émile Picard, in 1896. Then some of the manuscripts were published in 1907 and 1908 by Jules Tannery, and then there have been many reprints or re-editions since, culminating in the great Édition critique intégrale by Robert Borgna and Jean-Pierre Azra in 1962, just bringing together everything that we have in Galois' hand. Amazing edition. If you remember the headers that I gave you some time ago, there they are. I threatened or promised to talk about equations, because this is where Galois' work was revolutionary. So let's move to equations. This is the top of the first page of the Lettres Testamentaires, the testamentary letter. You can see he's written in the top left-hand corner, Lettre à Auguste Chevalier. So he has specified that this is what it is. And then you get the date, Paris, the 29th of May, 1831. The numbers on the right are library numbers. It's manuscript 2108 as the catalogue, and this is folio 8 of the manuscripts. But then there you see it, Mon cher ami, my dear friend, j'ai fait en analyse plusieurs choses nouvelles. I've done in analysis, but read algebra for analysis, really. The meaning of that word has changed over time. And actually at that time it had several different meanings. I've done several new things in analysis. Les unes concernent la théorie des équations. Some of them concern the theory of equations. And then he launches in and explains that he's been looking for the condition for an equation to be soluble by radicals. So let's think about equations. This is the moment where some of you may wish to think of dentists' drills and raising your hand, but I hope you won't. Here's an equation. Degree 1. What do we do with it? We learn at school that we can cheerfully divide by 5, because if 5 times something is 0, then the something is already 0. So if we divide by 5, we get the equation x minus 1 equals 0. X minus 2 equals 0. And we can pop the 2 over on the other side. We can add 2 to both sides and end up, if we haven't made a misprint, with a solution. Fine. Degree 2. Here's another one. Again, we'll divide by 5 and get the equation x squared minus 2x minus 1 equals 0. And then what do? In school we were taught at least I was taught 3 ways of handling such equations. One was to footle about looking for factorizations. And when I was at school, you would find them if and only if they were obvious. Second technique was to apply the formula that we chanted in school in order to learn it. If ax squared plus bx plus c equals 0, then x equals minus b plus or minus square root of b squared minus 4ac, and divide the whole lot by 2a. We were taught that in a sort of rhythmic form, which I cannot now remember. We were taught to learn that formula. Third method, which myself I find a little bit better, is to know why that one is true and actually complete the square. So when you've got x squared minus 2x minus 1 equals 0, that's x minus 1 squared equals 2, isn't it? You can't do it in your head, but I haven't written it down. I haven't got a blackboard here. So we end up with x is 1 plus root 2, or x is 1 minus root 2. Quadratic equations. They have a very confused and confusing history going back thousands of years. Cubic equations. They have a very interesting history going back many, many years, but solution of them goes back really only to the 16th century. And if I were to give you a similar equation to this one, would you have been able to solve it in school? Well, I certainly couldn't. It was an obvious challenge to an obnoxious brat like me, but I couldn't do it. And I'll show you why I couldn't do it. Now, hold hard to your seats. There's the general cubic equation, except that you notice I've already divided through by the leading coefficient the 5 that we had before. So it is x cubed plus bx squared plus cx plus d equals 0. So it's already been simplified. To solve it, what do? Well, you do a bit of arithmetic with the coefficients, b, c, and d. You create this new number p, which is minus 1/3 of b squared plus c. You create a new number q, which is 2/27 of b cubed minus 1/3 of bc plus d. You then take q squared plus 4/27 p cubed. This is known as the discriminant. You take that number and form its square root. You add and subtract it to minus q. Take a half. Take the cube roots of those two, add them together, add minus b, and if you've not done it wrong, you've probably got a solution to the equation. Compare that with your memory of the solution for a quadratic equation. There's well, people speak of a quantum leap, don't they, or a exponential growth or something. There is huge growth here, isn't there, in the complication. And you see, even if you take a simple equation like the one I've written down there, 5x cubed plus 10x squared minus 5x minus 5 equals 0, where you can straight away divide by 5, as with the quadratic and the linear equations that I gave you. Mark, were you holding your hand up? No. Oh, good. It's very worrying when professors hold their hands up. Of course, that is just the equation x cubed plus 2x squared minus x minus 1 equals 0. Very simple equation, isn't it? Right? X cubed plus 2x squared minus x minus 1 equals 0. The coefficients are really very small. But when you plug it into the formula, this is what you get, and there's a square root of minus 1,323 in there. Cubic equations, they're beautiful objects, but they can be quite uncomfortable bedfellows. Fine. Now, this was known by about 1545. What about quartics? Known very shortly afterwards in Italy. There is a similar formula. It's more complicated. You do a lot of arithmetic with the coefficients. You form a square root to create the analogue of that, where's it gone? The analogue of that discriminant that we had in there, the square root of q squared plus 4/27 p cubed. So you do a lot of arithmetic to get that discriminant. You take its square root. Then you do a lot more arithmetic with that and with the coefficients, and you extract a cube root. Then lots more arithmetic, extract a square root. And now if you're clever, you don't need more arithmetic, but normally you would do a bit more arithmetic, another square root, a bit more arithmetic, and you've got the answer. When you write it down on the page is not big enough. Well, unless you're the sort of person who can write the Bible on a stamp. So what about quintics and sextics? Well, I mean, these, as I said, were solved by the mid-16th century. And for 250 years, there were efforts to solve equations of degree 5, degree 6, and higher. Lots of efforts by lots of famous mathematicians. You won't find them in the usual history books because they didn't succeed. And one of the odd things about modern presentations of the history of mathematics is that they fall down in this way, that they only tell you about successes and not about failures. And the failures are often just as important as the successes. Well, so there were 200 years of effort. The general problem is this. We take a polynomial equation of degree n, I'm going to put it back into the generic form with ax to the n plus bx to the n minus 1 plus and so on, where a is not equal to 0, because after all, if a had been 0, you wouldn't have written it down, would you? You'd have had an equation of lower degree. And the classical problem was to find a formula involving those coefficients, a, b, c, and so on, rather like the classical one for quadratic equations that you all remember because you were made to remember it, or like this classical one for cubic equations, a formula that involves those coefficients combined with the operations, the arithmetical operations, plus, minus, multiply, divide, together with extracting kth roots for any k you wish. If you read some of those unsuccessful attempts at this problem, you will see that our colleagues of 300 years ago had the very reasonable insight that if what you've done to create the polynomial is to raise this unknown number to a power, x to the various powers, squared, cubed, and so on, x to the n, and then you've multiplied it, you've added, and so on, then it's not unreasonable to expect that you should be able to undo that by the inverse operations, that is to say, by division, subtraction, by extracting roots. But there is no such formula. There is no such formula for equations of degree 5, 6, 7, 65,537, though if you ever meet one of those, be a bit careful, won't you? There were efforts to prove that for some years after a great paper by Lagrange in 1770-71, finally proved satisfactorily by Niels Henrik Abel in 1824, not until he thought he'd got a solution for the quintic, I may say, published in 1826, and then he published further refinements of it. And if you want to know about this part of classical algebra, I can recommend to you this book. It's by my colleague at Queen's, Jacqueline Steadall, lecturer in the history of mathematics at Oxford, and a very good friend, so I should not be advertising her book, but it is an extremely good book, and it fills that gap that you will find in all other history books when they talk about algebra. From Cardano's great art, the Ars Magna, to Lagrange's Réflexions sur la résolution algébrique des équations. Let's move on. I want to move on to the questions that Galois tackled. And remember, we're dealing with a boy of 18 here, 17 and 18. Keep that in your mind when you find this a bit difficult. Suppose you have a particular equation with numerical coefficients. So I'm not talking about the generic equation here, just one of those equations that you bump across all the time on a dark night. The question is there a solution in terms of radicals, meaning a solution in terms of numbers that you obtain by starting from numbers that you know, the coefficients, other numbers like 1 and 0 and 27 and 65,537, doing arithmetical operations on them, such as multiplying, dividing, and so on, and doing radical operations, extracting roots. So you can get quite complicated numbers. Root 2 is the least complicated of all of them, even although we know that philosophically it was pretty complicated for many, many years. But you could take, for instance, I've written down there, form the square root of 5 subtracted off of 3 and form the fifth root of that. That kind of number. And your imagination can run wild on this. You can take roots of roots of roots of roots of roots. So you get lots of numbers. Well, there's an equation I've written down, x to the 5 minus 5x to the 4th plus 10x cubed minus 10x squared plus 5x minus 2 equals 0. Some of you have already spotted that that's x minus 1 to the 5th minus 1. Right? Fine. So x minus 1 to the 5th is equal to 1. Extract a fifth root of 1. Add 1 to it. You've got a root of that one. But what about this one? X to the 5 plus 10x squared minus 2 equals 0. It's one of the deep facts of mathematics that however you manipulate your numbers, whatever numbers you start with, whatever roots you take, you will never get to a number which is a root of that equation. That's not at all easy to prove, as final year examination candidates at Oxford and Cambridge find. This is, in fact, a finals question. Prove that this particular equation is not soluble by radicals. Not at all easy to do. It's advanced undergraduate work now, but the theory was created by a 17, 18-year-old. So I hope our undergraduates just feel a little bit overawed. There was the question, how are equations that are soluble by radicals distinguishable from those that are not? Because I was chattering so much, you probably didn't read what I had written in blue at the bottom of that screen. But I have repeated it here at the top of this screen. How are equations that are soluble by radicals distinguishable from those that are not? And Galois' answer was that, first of all, there is a group that is associated with every polynomial. The world did not know what a group was at that time, and half the world, more than half the world, does not know what a group is now, and probably shouldn't know either. I'll come back to that. Solubility by radicals can be expressed as a structural property of that group. Right? The group is now known as the Galois group of the polynomial. The theory is Galois theory, which, if you remember, I mentioned way back here when I was talking about the content of the premier mémoire. The second one down, Memoirs sur les conditions de résolubilité des équations by radicaux, the premier mémoire contains Galois theory of equations. That is what is in this paper. It's an amazing document. These manuscripts are, in fact, very, very moving. They're harsh mathematics, but they're very moving when you see them. They're getting very fragile now, and you work mainly from facsimiles if you're working on them. I'm very proud that after some while, I was given permission to work with the originals, which of course I did as little as possible because they're so fragile. But since June, mid-June this year, they have been mounted on the web. So you can see them, photographs of them, images of them, on the web, on the site of the Bibliothèque de l'Institut de France. And I'm very proud of that because that was my agency that got them there. Fine. So let's come back and see what are these groups. Well, I want to take you back even a little bit further, 15 years earlier, to some work of Augustin Louis Cauchy in 1815, his earliest work, really, apart from a paper on polyhedra. And he uses language this way. He calls a permutation the same as an arrangement, which is, of course, the English arrangement, just write your symbols down in a certain arrangement on the page. And a substitution is the change from one arrangement to another. For example, and this is his notation at that time, he changed it 30 years later, but the substitution here is the one where you substitute 5 for 3, 4 for 5, 3 for 2, you leave 1 unchanged, you substitute 2 for 4. Sorry. It's a little bit unfortunate that we now, and Galois then, confuse the words permutation and substitution. That is to say, we now use the word permutation in universities, though not in schools, for the dynamic act of changing from one arrangement to another. Of course, in schools, in the context of permutations and combinations, a permutation is the arrangement, same as Cauchy had it. So we're going to use the language this way. A permutation is an arrangement on the page. A substitution is something where the act of rearranging, getting a new permutation, a new arrangement from an old one. And this is what the referees, Poisson and Lacroix, saw in 1831. Now, I don't want you to read all that. It's the first proposition of the premier memoir. There are 4 lemmas that precede it. Let an equation be given which the m roots are ABC and so on. There will always be a group of permutations of the letters ABC with the following property. Every function of the roots invariant under the substitutions of this group will be rationally known conversely, and so on. Now, this is where the mathematics is getting a little bit more technical, isn't it? Those of you who have seen the beginnings of Galois theory will recognize this. It's the introduction of the Galois group. But in a different language that you do not recognize. And I'd like your hearts to go out to Poisson and Lacroix, because this is the first mention of groups in the premier memoir. And it's crucial for the theory. But they haven't been introduced before, so how did Poisson or Lacroix know what they were? Hadn't a hope. Hadn't a hope. Well, not unless they read further. They might have, they'll have read Proposition 1 and the preceding 4 lemmas. At the end of Proposition 1, Galois gives 2 examples, the so-called general equation of degree n and the cyclotomic equation. He then gives the proof of Proposition 1, and of course, because Proposition 1 involves these groups, you are working with them as you go through the proof. And then, at the end of that, there is a scholium, a remark, which is an exiguous explanation of groups. But Galois hasn't really explained himself very clearly, has he? I'm presenting this to you in a way that doesn't show him in a good light. That's not fair, is it? That's always the problem of history of mathematics, history of anything at all. That whoever tells you something as a historical fact is intruding interpretation. And I am doing that. On the other hand, I hope that, when you get a chance, you will look at what Galois wrote and see if you could have understood what Poisson and Lacroix had to understand without having studied group theory beforehand. Poisson and Lacroix saw the premier memoir in January 1831, reported on it on the 4th of July, 1831. In 1832, the night before he went off to be shot, Galois added a wonderful marginal note to Proposition 1. And that contains this, well, that is this note, you'll find it quite hard to read. If you can read it, you'll see that up at the top there, it says à reporter dans les définitions, to be moved to amongst the definitions, which are a few pages earlier. And in most of the editions, that is where it comes. In mine, I'm sorry to say it doesn't. I apologize for that. But the reason is that I've tried to be faithful to the manuscripts. So I'm trying to give you a print version of the manuscripts. That's almost impossible to do, and I should have accepted that, and should have carried out Galois' instructions to move it further forward. But since all other editors do, I decided, no, I'm going to stick with providing you with a copy of the manuscript as we know it. But with a lot of warnings, actually. Here it is translated, and time is running out, so I'm going to spare you going through it. The important thing to note at the end is this. You have a group of permutations. It has substitutions. And the crucial thing at the end is that if amongst those substitutions you have two of them, S and T, on est sûr d'avoir ST. ST. Was sure to have ST. So this is closure. And here it is in summary form. A group of substitutions is a collection of these substitutions, what we now unfortunately call permutations. It's a permutation group. Collection of substitutions with the property that whenever you've got two of them, do S, then do T, do S, then do T. The result, of course, is a new substitution. That substitution, that new substitution, will always also be in your collection, in your group. That is what is characteristic of Galois' group. The groupe de permutations is a collection of permutations, that is to say, of arrangements, that you get by starting from one arrangement A and just permuting it with all the substitutions S of that group of substitutions. That is the group of permutations. In the first instance, though, in that first memoir, the word group is an informal word. Remember, Galois' definition wasn't made until the eve of his duel. He was perpetrating definition by context. As you read the proofs and went on to the more sophisticated parts, the fundamental theorem of Galois theory, what happens when you adjoin all the roots of an auxiliary equation and so on, so that you get a normal subgroup and so on, you begin to understand what he's batting on about, but from context. But of course, from that, it gets its technical meaning. And then there is this wonderful criterion for solubility of an equation by radicals in terms of its structure, which I'm not going to tell you about. It is summarized in the Lettres testamentaires, summarized very beautifully, more beautifully than it is explained in the Premier Memoir. But it is a criterion in terms of these groups, the structure of these groups. It's an absolutely clear criterion. So what he gave us, this is his legacy. Groups, which, of course, huge subject now, what are called fields, these abstract algebraic entities where you have two operations, addition, multiplication, and the usual rules of arithmetic apply. Galois theory, which is the modern theory of equations, and this became the beginnings of modern algebra or abstract algebra. There are many myths and mysteries still. It's a myth that Galois invented group theory on the night before the duel. In fact, he even published the word 2 years earlier in the paper sur la théorie des nombres. The word is used in the sense of the Premier Memoir. But remember, he'd written his theory down already in May and June 1829. So the Premier Memoir is a rehash of what he'd already written earlier. So these things were clear in his mind for 2 or 3 years. It's a myth that Galois knew and used the simplicity of the alternating groups. Now, this is something which many of you won't mean anything to some of you, but will mean something to those of you who have claimed that he did. It's nonsense. There are some mysteries. 2 years before his death, he doesn't seem to be doing any mathematics. He got involved in this incompetent republicanism. He had all these wonderful ideas which he described in the Lettres testamentaires. Didn't write them down. 2 wasted years. Really, everything we have of any value from Galois was written in the 13 months fore and aft of his 18th birthday. And he died aged 20. But then there's another mystery. Galois died in 1832. His Lettres testamentaires was published in September 1832 by Chevalier as Galois had commanded. In that letter, Galois appoints Chevalier as his literary executor and commands him, really, to publish the letter, which indeed Chevalier did in the Revue Encyclopédique for September 1832. But nobody noticed it. No reaction to it. 1843, Chevalier got Joseph Liouville interested in the manuscripts. 11 years after the duel. And it took Liouville 3 years to understand what was going on, but he published them in 1846. But there are a lot of questions about this. First of all, why did nobody else show an interest? Well, because it was all very difficult. But secondly, why did Liouville suddenly understand it and then publish it? There's something very, very odd about this. And my colleague in Paris, Caroline Erhardt, has written a very interesting paper about that with the wonderful title, La naissance posthume d'Évariste Galois, the posthumous birth of Évariste Galois. Wonderful title, and she tries to treat this problem. Anyway, these are the things that I've been excited by. Here he is again, Évariste Galois, géomètre révolutionnaire. Thank you very much.